What is up, most distinguished patrons of this channel? So for today's video, we're going to be diving into the question on everyone's mind, well, on a lot of people lately that have asked me, and that is, what is the practical limit of the short circuit, short arc MIG process when it comes to what material thickness you can weld? And the answer is it's kind of far more complex than you would think. And we're going to dive into everything to do with this to where you have a better understanding of both what the process limits are and what your equipment limits are, because sometimes those are two different things. So with that said, let's get into it. So I've wanted to do a video on this topic for a while now, and for some reason, it's weird how the internet works. I had 5 random comments all in a roundabout way pointing to the same thing, which is basically, what are the limits of the short circuit MIG process? And I thought, well, I kind of touched on this a little bit in random videos, but I've never done it directly. So we're going to explore everything to do with that today. Now, the truth is a short circuit MIG process is actually a little bit different than basically any other welding processes, and I'll show you why that is in a minute. But what you need to understand is welding processes have limits to what they can do. And one of the biggest limits in the case of short circuit MIG is how thick a steel it can weld. It has a hard limit. That hard limit is generally, for industry concerns, is generally considered 5/16 of an inch, so just under 3/8 of an inch. Now that doesn't mean that a job or some manufacturing plant wouldn't use short circuit to weld, say, 2-inch thick steel. It's entirely possible. But what I'm saying is, for code work, for high reliability stuff, etc., you get the picture. It's generally not used above 5/16, and generally for you at home, because most of you probably have 200 amp capable MIG welders and not, say, a 250 or 300 amp capable, you should be looking at the processes handling 1/4 inch and thinner material. And in the testing today, you'll come to an understanding of why I say that. So with that said, let's go and do some book learning and define what short circuit MIG is, and we're going to look at the limits and why they are the way they are, as well as why it's different than a lot of other welding processes. So the first thing you need to understand is the short circuit or short arc MIG process is a gas shielded wire process. We are not talking about flux core here. And the short arc process gets that name because more or less the wire that's fed out of the MIG gun enters the weld pool, or in the case that there is no weld pool, it hits the plate and it's a solid. So that wire remains as one piece, it stabs into that plate, it shorts out the wire, and the wire blows apart, and more or less you have an arc that intermittently exists between the area the wire blows apart and your molten pool or your plate. So it's called a short arc because, well, there is a short arc, but that arc exists when you're welding and you have a weld pool created more or less between almost the tip of the wire and the molten pool. So that arc exists quite a decent distance away from that plate. And that's why in a lot of videos I mentioned that, like, dragging with the short circuit process generally will produce a little bit more penetration, and that's because the molten puddle is being pushed away from your arc, and your arc exists more or less down here instead of on top of the puddle. When you push, it's very easy to ride the puddle, and thus you have your arc and all of that heat up here, not closer to the steel. But the short arc MIG process is excellent for welding everything from like 22, 24 gauge steel on up to 1/4 inch reliably. When you get above a 1/4 inch for thickness, depending on the joint style, you can suffer what's called a lack of fusion. It's really joint dependent, and you're going to see in this video that some situations are far better for short circuit to attempt to weld thicker material than others. But universally, for a 200 amp home hobby type level machine, you should be looking at 1/4 inch as your maximum and only weld thicker than that on an as-needed basis depending on a joint style, or switch to a different process. Now, the short arc process is primarily done with 200 amp and less machines, and it's done with either 100% CO2 gas or C25 argon CO2 mix. There's another way, if you have a powerful enough machine, to use the same wire as short circuit and gain a lot more performance, aka root penetration, root fusion, sidewall fusion potentially as well, and that is to switch to a different method of transfer. I have a whole video on spray arc if you're interested in it, on what it is, how it works. The link is in the description. Now with spray arc, you're using the same wire as short arc and possibly the same machine if your machine is roughly capable of 220 amps and 27 volts or so. It has more to do with being capable of putting enough voltage out than amperage. It's the voltage that pushes things into spray mode, along with a special gas mixture. Now with spray arc, the tip of the wire never comes in contact with the plate like the short arc process does constantly. It liquefies into small droplets, the wire does, and then basically transfers over in the arc. Now with spray arc, you have a arc that's existing, much like poorly drawn right here. There's an arc that exists separate from the molten metal. The metal is merely transferring over through that arc, and that arc is very aggressive. There's a ton of heat, and because of that, even though this has a higher metal deposition speed than with short arc, because of your wire feed is being run way high, sky high, that arc being separate from the wire, where, as you can see here, the arc is actually nipping away at either the plate or very little molten pool as you're going, is a complete direct contrast to the arc existing more or less inside or above your molten puddle. Therefore, you typically get a lot more aggressive penetration and fusion, root fusion, with this process over short circuit. And that is also why that this process, because the arc to metal ratio tends to favor arc more than the metal, this produces on thicker material far more favorable results in short circuit, short arc. Now there's a third method with the MIG process that's not very common but is similar to spray, and that is globular. What globular is very high voltage in settings with 100% CO2 gas. Now, I've shown in the past, and I'll put a link in the description to this video, 100% CO2 with the short arc process actually improves penetration significantly over C25. Well, if you crank those values up even higher, you get into what's called globular, where more or less, think of it as a coarse spray. The wire is not coming in contact with the base material anymore, and it's balling up into big globs of metal and transferring over. You have an extremely aggressive arc in this method, and unfortunately a ton of spatter, and it's not really commonly used, but this is a distinct method of transfer that is different than short arc. Now, the reason I brought these up is so that you understand that if you're in the short arc process, which means that you're typically below 200, 215 amps, maybe a little bit more depending, under about 23 volts, and you're using C25 or 100% CO2 gas, you are running in the short arc process. If you're running 25 to maybe 30 volts and you're running spray mixture, then you can spray globular 100% CO2, you get that. But what you need to understand is that these processes here produce more root fusion, more sidewall fusion typically, and just overall better performance on thick steel that you simply can't get from the short arc process because of how the heat input works. Worst case scenario with the short arc process, if you were to try and weld, say, 1-inch thick steel, what will end up happening is the weld will bridge over the root completely. This is your weld, and it will not fuse anything down here in the root. I'll draw a little. It will not fuse anything here, and this is a bit exaggerated, but you don't have any fusion, and that's very typical of that process, and there really isn't any magic on getting around that, unfortunately. I've done videos, links in the description, dealing with preheating and how that doesn't affect short arc MIG's ability to penetrate anything. It just makes the weld look hotter and flatter, but it still doesn't penetrate. And I've also done a video on beveling and how in many joint styles, in many cases, that simply is ineffective, because if it won't fuse anything on thicker plate, beveling it down a knife edge on one member, like say on this, if you were to bevel this to a knife edge, you're still not going to fuse into the thicker material. You might get better fusion here, but that's it. So even that isn't a solution. The short arc process is really, again, I'm not beating a dead horse here, should be used on 1/4 inch and down steel if you have a 200 amp machine. And if you decide to weld thicker than that, you need to do some test joints and see what the penetration is and make a determination if that is acceptable, because you will lose penetration when you start talking 5/16, 3/8, or anything thicker than that. Now, because this is all relevant, let's talk about why the short arc process has limitations that stick TIG don't. Depicted here is stick welding and TIG welding. You'll have to mind my poor drawings. So as we established, your arc exists more or less in the middle of the puddle or the top of your molten puddle to the wire, and the heat input is pretty far away from the actual base material. With stick welding, it functions more like a globular transfer, like we talked about with 100% CO2. You have bigger hunks or balls of metal, and then you have an actual arc present in those balls of metal. Therefore, that arc has a much easier time actually hitting your base material instead of trying to get through and melt through molten metal. And that's, again, going back to the short circuit process. The higher your wire feed speed, the higher the risk you have of producing a tall bead, especially if your voltage isn't up high enough. And then you have that much more material to attempt to get your heat to go through in order to hit the base material. Well, with stick, you just don't have that issue because, again, it's similar to globular. Now with TIG, you have basically a tungsten and an arc, and then you add filler wire manually. Therefore, your arc is always on that base material, and the only time you tend to have lack of fusion with TIG is running too low an amperage and doing something like lay wiring or pushing too much filler, where the puddle goes cold and then it doesn't fuse into a root. But because you have basically an arc on its own, you can achieve 100% root fusion without issue, because, well, you're welding directly there. All of the heat is right here instead of right here. And that is why the stick process and the TIG process arguably have no limitation on the thickness of material they can weld. You're probably wondering, well, with the MIG process, I just multiple pass everything and it's fine. Well, again, you know, multiple pass means you're putting a weld that is thick enough for the thickness of material. So say you had 1 inch thick material, that you have a 1 inch thick toe to root weld. Well, yeah, that is putting the appropriate size of material of weld down for the material you're welding. But if you have very poor sidewall fusion where it's like not bit into the plate, more weld doesn't solve that. Not to mention, again, if your weld looks something like this where it never fused the root, guess what? If this were to ever get bent this way, it's going to tear and the weld will fail very easily, versus if you had a weld that looks something like this where it penetrated and fused all of this in. And that's the point that I'm trying to get across. Now that you understand more about this, let's look at the setup that I'm going to have for testing all of this so that we're all on the same page. So here are all of our test welds, and I may add another one, we'll see on that. We have 1/4 inch material here. This is 3/8. This is 3/8 plate, both knife edge beveled and on a 1/4 inch backing strip. These are all prepped to bright, shiny, clean material, and that is a very important thing. If you're going to be doing short arc MIG on anything, even 1/4 inch and above, you need to surface prep your stuff. If you don't, and you have that mill scale, it's very common to get a lack of fusion because it doesn't penetrate very well through that scale, and that is part of why you see a lot of failed MIG welds, short arc MIG welds on thicker material, is due to poor prep. That will play a role. Now what we're going to be doing on this guy here, it's just a standard fillet weld 1/4 inch. We're going to take this 3/8 plate, we're going to do the same thing on one side, and then on the other side I'm going to turn the settings up even higher to something in the 225, 230 amp range and see if our results are even any better. And my anticipation is that we'll deposit a bigger weld possibly, but the root fusion is not going to be better with higher settings due to the limits of the process, not the amperage. Now this is a sort of replica of like a structural steel type situation where you have that backing bar and 2 3/8 plates. Now, truth be told, I am certified in the state of Wisconsin for structural steel, so I had to weld one of these that was a little bit longer, vertical up and overhead, and it had to pass a bend test, multiple cutouts from it. So with 7018 all the way out. I have never attempted to do this with the short arc process, and my anticipation is it very well might actually bite into stuff on this. And the reason is simple. This wide open bevel gives a very good place for the molten metal to spread out and thin out. And that's one of the biggest issues, like on fillet welds on thick material like this, that molten metal is more or less pushed into a corner and becomes extremely difficult for that arc to put enough heat into that to melt it. Well, with this, where you have the bevels and the molten puddle can grow and thin out, I think the fusion's going to be better. Now, I will be pulling all of these welds in an attempt to maximize penetration. In a case of this, I'm undetermined at this point if I'm going to put a cap on it or not because it's really of no consequence. I probably will, but I'm going to try and do as many stringers as possible. If the stringers don't look like they're going to work, aka they're too tight and it's going to create a lack of fusion, I'll just do a weave pass somewhere on the fill, but we'll have to see what we get out of this one. This is pretty uncommon. I'm unaware, and please correct me if I'm wrong, but I am unaware of any certified procedure that would be for 3/8 plate, 1/4 inch backing strip that would use short circuit MIG. I don't know that a certified procedure outside of maybe pipe would exist on something like this. And on pipe, you're doing open root. And a pipe isn't structural, if you understand what I'm saying. Like, you don't weld a bunch of pipe for the sake of putting massive amounts of weight on it. I mean, structural tube or something, sure, but you know, pipe world is totally different. On a structural type situation, I can't imagine too many companies would be attempting to do this and sell it as a quality job with the short circuit process. Anyways, all of these will be welded in a flat position. I could do them vertical up, which would actually increase penetration, but I know that a lot of you out there probably can't weld vertical up with short circuit MIG very well, so I'm going to kind of replicate what you might do in your home shop where you're welding in a flat position. All right, let's start out by welding that 1/4 inch. All right, I had to take a break and let this crap cool because it's about 100 degrees in here, and I'll tell you what, I should have took that into account when I was welding all these multi-pass welds, man. I got smoked hot. Anyways, I let this stuff cool down, cut and etched it, got some water, and now that I'm hydrated and feeling a lot better, let's take a look at the results. So let's start with this 1/4 inch plate and take a look at what the cut and etch says. So looking at this, everything looks really good. The sidewall fusion near the toe of the weld is a little bit less than I would like to see, but this is exactly what you can expect from the short arc MIG process. It tends to favor a little bit more of the root penetration over sidewall. When you use like 7018 stick rods, it tends to be a more rounded weld nugget per se, but this looks good. And definitely the short arc process can weld 1/4 inch steel with a 200 amp machine. Now keep in mind, if you plan on doing a lot of 1/4 inch material, a 200 amp max machine will probably hit thermal overload, or you'll start having things melt in the gun if you do a lot of it. So you want to be careful with that. That's probably the biggest drawback of the short arc MIG process, is that simply a 200 amp, which is your common MIG welder sold at stores that many of you have, is basically maxed out just to weld 1/4 inch thick steel. It's just the reality of the situation, and that's why stick tends to be a better solution, because you can actually get some duty cycle output without hitting thermal overload welding 1/4 inch, because you're only at like 90 amps output to get the same results with stick. And that's why I stress so much to people out there that if you really want a MIG machine, a wire welder that's capable of welding a lot of, say, thicker material, 1/4 inch, maybe a little bit thicker, you really need to be at a 235 to 285 amp machine. And then you eliminate basically all the issues that the smaller 200 amp or sub 200 amp machines have. So as you saw the cut and etch on 1/4, definitely no problem with the settings that I ran and the machine that I was running it on. This is basically easy work for it. And like I tell everyone kind of in the comments, is that 1/4 inch plate for the short circuit MIG process, provided you have a 200 to 225 amp legit capable machine, is really no issue. And in a lot of cases, this would provide more root fusion necessarily, or penetration, than stick with 7018. The difference is, though, keep in mind, this is perfectly clean steel. This is the ideal circumstances. Where 7018 is going to come out ahead is when you're welding on crusty, rusty stuff. You're going to start getting weld defects and porosity and other issues on that with the short circuit MIG over stick. But for clean metal, it's more than adequately strong enough and penetrates perfectly fine, as you saw. So now let's take a look at this 3/8 plate. On this side, I ran the same settings as the 1/4 inch plate, which is basically 100% maxed out on a 200 amp machine. That would be the most you could get out of it. And I ran a pass, and then I ran it at what Miller Electric would suggest for 3/8, which was a significant bump up. I'll put the settings when we look at both of them. But these actually kind of surprised me a little bit better than I expected. But let's take a look at it. So the weld on the left was done at reduced settings, the weld on the right was done at increased settings, and we'll look at what those settings are in a minute. The colder weld on the left side has a very straight, flat fusion line that's in line with the plate, and anytime you start seeing things like that, it's suspect that there's going to be a lack of fusion there. Keep in mind, this is one location cut and etch on this plate. The fusion will change depending on where you cut it on the plate. The closer you are to the start, the worse the lack of fusion will be. The longer you go closer to the edge, it'll typically improve a little bit, simply because there's less metal to absorb the heat, and it will tend to fuse a little bit better. But the weld on the left I don't like. The weld on the right isn't too bad at all. Keep in mind, the one on the right was done at very high settings that are beyond any 200 amp home hobby machine. So you can see the settings there, and I kind of highlighted the little areas with red that are suspect that I don't like, especially on that bottom of the weld on the left. Now 430 inches a minute and 22 volts is in the ballpark of what you might be able to achieve with a 200 amp machine. Keep in mind that this is 035 wire, and the amperage output somewhere around 200 amps, and your average home hobby machine isn't going to like these settings for too long, to be honest with you. And I'm running on a machine capable of 250 amps, so it's really no sweat for it to run this. Now on the right side, the 480 inches a minute, 23 volts, somewhere in the neighborhood of 210 plus output amps. The weld overall looks a lot better. Yes, there's a straight line on the right, however, that's into the plate. That's a decent fusion line. It broke down into the plate. The upright plate could be a little bit better on that area where it kind of slopes a little bit in towards the face, but this is, again, short circuit MIG. This is about the best that you're going to see on 3/8 plate. The big issue I have with what's going on here is the unreliability. And what I mean is, yeah, this cut and etch looks okay on the right, and I think those settings would be acceptable to weld 3/8 steel. But again, this is a flat position. Who knows what it would do in overhead? Who knows what it would do on mill scale or dirty material and used material, like in the repair world, say on some excavator or something. The results are just unpredictable. And this cut and etch, you know, who knows what it is near the start. It could be significantly worse, like on the left side weld, than what we see here. And that's why it's predominantly not used for thicker steel, is just the results on a cut and etch on a test weld is one thing, but the reality of the real world is another. So the colder settings, aka the maxed out 200 amp MIG welder, are a little bit suspect. They're not bad. I mean, the penetration is decent, but I don't like seeing straight lines on a sidewall as much as I saw on that, and that's a little bit more suspect to me. Now, the higher, hotter settings definitely overall were better. Keep in mind that those settings were probably in the ballpark of 220 amps. I mean, when you start talking 470 inches a minute and 23 volts, I mean, you're up there. I mean, it almost doesn't sound like short circuit anymore. And the performance is there on 3/8. But again, I wouldn't necessarily want to make a habit out of it on 3/8, and definitely not on anything thicker than 3/8, simply because of the issues that you have where if it isn't perfectly surface prepped, etc., you might run into issues. But is it capable of a fillet weld on 3/8? Yes, it is. Is your machine capable? Probably not, unless you have enough power to be getting up to these values that I ran the second one at. The other thing you guys got to consider with this, and like I mentioned earlier, I did a drag angle on all of these for the sole purpose of attempting to get as much penetration as possible. If you were to push this, I guarantee you your penetration would be worse and way more suspect. Not to mention the technique that I weld, where I go straight in and just do a smooth drag angle. A lot of guys out there like to do this circle ease and start spreading the heat over a large area. And I'm telling you, do a cut and etch on stuff like that on thick plate. You're going to see that manipulating it wider, often you get better sidewall fusion, but your depth of penetration in the root is worse. So that's something to be highly suspect of. So on a structural steel coupon we got here, everything kind of went okay, just okay. The fill passes, everything was all right. When I went to cap it, I had overfilled it a little bit, therefore I didn't have a guide to weld to, and the bead, I kind of overlapped this bead on top of the other bead a little bit, but it doesn't really matter since we're not bend testing it anyways. But based on the overall appearance, I cut it here. The metal went in pretty clean. I didn't really notice anything abnormal or unusual when I was welding it. And I did use a drag angle for each one. I let it cool a little bit, just a little bit between passes. Let's take a look and talk about these results. So here we have the multi-pass weld, and the first thing that kind of struck me as interesting was that it actually penetrated into the backing strip pretty decent. That's more than I would have expected, so that looks good. What I don't like about this is on the right side of that, there's an absolute straight line, and to me, that's guaranteed lack of fusion there. And that's why with MIG welding tests, like on pipe, they actually, rather than doing an x-ray, they bend test it, because something like that might pass x-ray, but when you bend it, it fails because what appears to be fused, even on an x-ray, might not be. So that super straight original bevel edge there is highly suspect. Everything else doesn't look too bad. The cap's a little excessively tall, and that's my bad on that, but the left side is actually better than I would have thought. And keep in mind, these are settings that would max out a 200 amp MIG welder. So this is about the best results you're probably going to get. And this is also going to be highly variable. This is in the middle of the plate. The start and end will likely look different than this. So here we can see the passes that I put down. One is the initial root pass, 2, I weaved over that with a hot pass, and then 3 and 4 were the fill passes. If you notice, both 3 and 4 are less in width than number 2. You want to avoid putting a stringer in for like number 2. The reason's simple. If you put one stringer, what's left to weld is so narrow that you're going to end up getting a lack of fusion at the root of that, weakening the joint. So generally, like, your second pass is going to be a weave, even with stick, wire welding TIG, same deal there. Now, pass number 3 is a stringer, and then number 4 is a very small weave. As you can see, size-wise, it's between pass 3 and 2. Again, this doesn't look that bad other than the area by number 4 and a little bit below that. I don't like the way that that looks. That's generally not a good sign. Even part of 7 has a straight line in it, so that's undesirable. Well, let's look at the other side of the cut and etch. This is where things get interesting. What appeared to be a possible lack of fusion on the other side of the plate is an actual lack of fusion on this side. And this is only about an 1/8 inch away, because you got to assume the saw blade cut plus the polishing and etching of it. And this is clearly a lack of fusion. This is going to be very common with the short arc MIG process on thicker plate. Now, all of these passes, I did a drag angle and kept the gun parallel with the joint. I wasn't like focusing the wire on the sidewall at all. Had I changed the technique slightly, this might not have happened. But again, it goes back to what I said earlier, that the short circuit MIG process is just unreliable at achieving sidewall fusion. And who knows, I didn't cut this plate in more places than what you see here, but it's entirely possible an inch from this point looks completely different. The biggest problem with what we see here is that this is going to be a common occurrence, and you as a welder will never know that this is there unless you're doing some kind of x-ray or ultrasound or something, which obviously you're not doing. So if you go and repair 3/8 plate with a backing strip, it's entirely possible that the weld will fail under stress because you have stuff like this inside of it. Not to mention, you might do a test weld on perfectly clean material and then go and do this on something that's less than perfect and have a completely different result. And visually, you can't tell that this is going on, even in between passes. Like, there's no indication that this exists. And that's where the biggest issue is with this. There's no way to know without actual, like, radiographic x-ray testing that this happens. Now, as far as how weak this is, if this was on like an excavator arm or something and it was stressed, more than likely a crack will propagate right through there and your weld will fail. I mean, this is probably 1/3 of the thickness of the weld is suspect on this. That's definitely not good, because if the weld isn't fused in and attached to anything, you don't have any strength. So the structural weld here, the performance was a little bit lackluster. And unfortunately, with the short circuit process, it really has questionable sidewall fusion at times. Even spray art can have questionable sidewall fusion. And based on what I see here, this is kind of what I expected. Now, it always goes back to the, well, I could have changed my gun angle, could have changed my travel speed, all of those things. And here's the deal on that, and I hate to be so blunt. You know, I've heard it a lot in videos where people comment with the short circuit videos I've done, where they say, well, if I would have just ran this setting, did this technique, or did this, that all the problems would be solved. And to a certain extent, you would be right. There are techniques you can do, such as I could have welded this vertical up and likely had far better sidewall fusion, right? So yes, you can do certain things, but if an average person, and I'm at no means an average skill, I'm above average skill with wire welding. I do hold a couple certs with it, by the way, but on a flat position, if I can't achieve reliable sidewall fusion by doing a drag angle and doing everything pretty close to right, then someone with your home hobby machine, 200 amp machine, is basically got no hope on this. And that's kind of what I'm getting at is, you know, relying on some magical technique or magical setting to make everything work is basically a way of saying, well, yeah, 90% of the time it doesn't work, but maybe 10% of the time it will. It's just not reliable. So, what did we learn today? Well, we did a small experiment dealing with the short circuit MIG process and looked at results on varying thicknesses of material, and we had varying results. And the key takeaway that I want to instill in you guys is that the short circuit MIG process is an extremely strong, reliable process when you have a properly sized welder, aka 200 amp class machine. Because trust me, if you were attempting any of this with a 140 amp machine, I don't care if you preheated the steel to 2000 degrees, you wouldn't even get close to these results. But anyways, it's a very reliable process when you're talking 1/4 inch and thinner steel, which guess what? That's a majority of what you guys probably weld at home. Rarely would you guys probably be welding 1/2 inch thick or 3/8 steel, but in the event you are, you must understand the limitations of both your machine as well as the process. And based on what I saw here today, kind of coincides with what I've seen in testing and just being in welding school in the past, and you name it, is that the short circuit process on 3/8 can produce strong welds under ideal circumstances, so proper fusion on very clean material with excellent technique, okay? But can it do it reliably under realistic circumstances, meaning maybe you didn't clean the mill scale off, or maybe your technique isn't quite as steady as mine? The answer is no. When you introduce any more variables than what we have here in this video, your results are going to be less. And as we saw in this plate test here, the results really aren't good. It's not something that I would like to see when you get that bad of a lack of fusion. And again, what can you do to fix that? Well, I don't know that increasing the settings any more than where they're at is really going to solve that. You can't go by visual look. I mean, no, this doesn't look perfect, but everything other than the cap looked like money. And guess what? It really wasn't. And what I'm really getting at, guys, is you have to test what you're doing. I don't care what I say or what anyone else says. If you think that you can weld this properly with proper fusion, do a test weld, try it, cut and etch it, and you might be surprised at what you see inside, and you don't want to see some of the things that we saw in this video. So with that said, hopefully you learned something. If you got any comments, questions, thoughts on this, feel free to leave them. Until next time.